conservation of built heritage always presents problems. Like all stonework, these iconic buildings will be subject to normal elemental forces, made worse by the increasing impacts of the longer, wetter, warmer winters predicted by climate change scientists. At the same time, the delicacy of the ancient stone demands that only non-invasive techniques can be used. A tall order, but at Queen's University, the challenge is being met.
So this is our 3D laser object scanner. It's used for very high resolution scanning, sub-millimeter in general. We use it to capture very high detail on objects. The first thing we do is we set the object we wish to scan approximately half a meter, 1 meter from the laser scanner. We then rotate the laser scanner so that we get the object in the center of the picture on the laptop, and then we get it to scan the object. It uses laser triangulation, where it shoots a laser from the bottom of the camera here, it hits the object and returns to the top, and at that time of flight it tells you the distance the object is, or the surface you're capturing from the scanner, and then it generates a surface on the computer. It does this using 4 laser sweeps, each increasing in strength. A very weak laser initially that comes off the more reflective surfaces of the object. The second, third and fourth getting increasingly stronger, capturing information from darker surfaces where that weaker laser wouldn't return. After it's done the 4th laser sweep, it also captures a digital photograph of what you've just taken, which can be mapped onto that scan.
This process is repeated as many times as are needed to cover the entire surface of the object, and the scans are then stitched together to complete the picture.
You can see the level of detail that this scanner is capable of capturing on a surface. This is called a TIN surface, T-I-N, which stands for Triangulated Irregular Network. And it's basically a series of triangles that are joined together. So when we rotate round to the back, we can see all these little triangles that are making up this tinned surface.
And the good news is that if repairs or even replacements to the stonework are needed, the hands-off approach continues.
This is part of Queen's building, and we can generate a 3D digital model of it using this technology, which can then be sent to stonemasons who can make a replica to the millimeter of this, and then obviously put that replica back on the building.
And the team have another, larger scale problem solver. This is LiDAR, which stands for Light, Distance and Ranging.
It works on the principle that a laser is generated in the bottom of the machine and comes up and hits this mirror you can see in the front lens. And when the machine is operating, we'll see this lens flick backward and forward. The machine then rotates fully through 360 degrees. It captures 2,500 points per second, which is relatively slow. There are newer machines out that capture up to 1 million points per second, but still exactly the same principle. And all you need is to connect it to a small laptop, and you can view the data coming in real time.
LiDAR technology has proved itself in the natural world too. This is a fly-through of Fermana's Marble Arch cave system. But LiDAR produces results that are not only fascinating for their own sake, the technology also offers highly valuable practical benefits.
Primarily in the commercial market, it's used for doing very accurate 3-dimensional drawings or creating 3-dimensional models of buildings. But in the scientific world, we can use it to monitor buildings as well and study decay on buildings, as well as physically capturing X, Y and Z coordinates on the surface of the building. It also records a reflectance value of the surface, and this is very useful.
Initially we thought there would be very little change on these surfaces, but what we have actually found is that quite a lot of material is being lost from these blocks per annum, and we're able to calculate that volume loss using this very high resolution technology.